Welcome to video 2 of class 1. Alright, so I want to just kind of go through a little brief history of fluid mechanics. It's kind of interesting stuff. You don't necessarily need to write a lot down for this, but it's good to know where some of these things came from. I don't know if I want to talk about, these are slides that come with the textbook. I don't know if I necessarily want to go through them. This guy right here, he's an important dude. Osborne Reynolds. Reynolds number is one of the really most important non-dimensional numbers that you'll run across and use to try to use previous experimental data for what you need it for. Reynolds number is also a measure of whether something is laminar or turbulent. So this is a little test thing, apparently, that a little test apparatus to show the transition from laminar to turbulent flow in pipes. So we'll see Reynolds number a lot in things. So that's the guy. I'd never seen a picture of him before. Things that important in the history of forever were the Wright brothers' a flight at Kitty Hawk in terms of aerodynamics. And aeronautics, right? Ability to fly. There's a picture of some wind turbines and a little wind, an old wind. People say windmill, but I think you actually have to be milling something, which is to like crush a grain and make it into flour for it to be a windmill. That's my opinion. You shouldn't call it a windmill unless it's like actually milling something. But never mind. So let's see. I have this in my notes right here. Some important people: Da Vinci, Newton, Bernoulli. He's our man. Mach, as in the Mach number. Osborne Reynolds. He looks a lot better in that other picture. In fact, I don't know. Is that actually that other guy? Now I'm starting to question if that was actually Osborne Reynolds, because that looks he looks like that should be like in the 19 or maybe the 1860s, or like when photographs were just invented. And this dude, that's not like in 1975. No, oh yeah, that is 1975. That's John Leinard. Okay, you should really read. Reading is important. So that was not Osborne. I wouldn't have thought so. Anyway, Reynolds numbers are really important. So just looking through some of this timeline, what Da Vinci contributed here is he did a lot of his initial sketches of different. He studied fluid flow phenomenon, and he would make little sketches and drawing of it and start to pick it apart. Starting to think deeply about how that works. Galileo, he did a lot of experiments. Of all kinds of things, right? These guys are famous for lots of other things, but in terms of fluids, he did a lot of experiments. Newton, what his real big contribution is, he really formalized and put down like some things that other people had been working on, but he really formalized it with his first and most important publication there. Anyway, so Bernoulli, there's actually a kind of cool stories about Bernoulli. I don't want to bore you, but he's from a family of like big time scientists and mathematicians, and his own father tried to steal his work. That's kind of interesting, right? But there's other Bernoullis, right? So it's interesting thing to look up and read the story of these. Euler, or Euler, I don't want to call him Euler, but the people pronounce it Euler. Incredible mathematician, and actually can be credited for taking Newton's stuff and actually making equations out of them that we could use. So F equals ma is actually more of an Euler thing than it is a Newton thing. Interesting. We got Navier and his buddy Stokes right there, right? So I mentioned the Bernoulli equation as being one of the very most important fluid mechanics equations, because it does a good job of relating pressure and velocity together. And that's one of our main goals, is to try to find a relationship between a pressure and velocity, because that's really what drives fluids to move, is a pressure differential. And so if you could figure out, we have this pressure differential and we're going to have this amount of motion, and you can find that relationship, you can solve problems. But it has limits. It would be only for inviscid things, right? So we couldn't, viscosity effects aren't included here. Well, Navier and Stokes, they, I wouldn't say they built off of it, but there you could make an argument that their main equation, the famous Navier-Stokes equation, which doesn't have a complete solution to it, right? So we can solve certain conditions for the Navier-Stokes equations, but we can't generalize and find a general solution for it. And there's some kind of prize if you can find a closed form, that's what I was looking for, a closed form mathematical solution to the Navier-Stokes equation. Mach is most famously known for this Mach number, and so he studied supersonic motion. I'm going to mispronounce this guy's name. I'm going to say Poiseuille. But anyway, he studied capillary tube action. And we already mentioned Reynolds number, so there's a lot about a turbulent flow going on here. Prandtl, I believe there's a boundary layer. We know a lot about boundary layers. You might recognize his name also from heat transfer. I think he's got a non-dimensional name named after him. Oh, by the way, he has a non-dimensional parameter named after him, Mach number. He's got a non-dimensional parameter named after him. He has a non-dimensional parameter. These non-dimensional numbers are going to be something that comes up later in the semester. We got von Karman. I believe he studied the wake phenomenon. That behind ships and boats, the wake, that's the trailing of the fluid and how that affects the motion. We also have Taylor. He studied waves. Right, so that's kind of interesting. He was renowned for studying waves. So anyway, these is important people that helped contribute and give a little bit of historical background. And I spent 7 minutes on that, so it's kind of boring, I know. So here's actually probably the more important thing that you want to probably skip to. I should have gone right to it. Is the no-slip condition is an important concept, important idea in fluid mechanics, and it relates to a very important thing called viscosity. That's I mentioned that the Bernoulli does not include viscosity, whereas Navier-Stokes does, right? So if the viscosity of a fluid enters into that relationship between pressure and flow, you can't use Bernoulli. You have to use something else, right? So we'll see. We have some workarounds in that. But we have to ask this question: what is viscosity? And so I would first start out with stickiness of a fluid, right? Or resistance to flow. Or another way to say it, it's a measure of resistance to shear forces, shear stress, whatever, being placed on there. Remember from the first video, the definition of a fluid is a substance that cannot sustain a shear. So if a shear is applied to the substance, it can't get into equilibrium. It will move, right? It won't stay stationary. Other things we want to know about viscosity, maybe right from the beginning, so that this is just the introduction to this. We're all going to come back to all of these topics over and over again. But just in the introduction of viscosity, we should remember that it's very sensitive. This property of the fluid is very sensitive to temperature. And so you could kind of you could imagine that, right? Think about maple syrup, and think about how it resists flowing as temperature. As you pour it out, it's slow and it's runny and it's sticky, right? But if you were to heat it up, it would flow a lot easier, a lot faster. Well, that's viscosity, right? And way that we will often measure, so I wrote this down on my notes, we'll often measure viscosity by timing how long it takes to flow through a nozzle, or let's say through a funnel. So if you can picture that, you can start to understand viscosity. But the whole topic here is the no-slip condition. Well, how is that related to viscosity? Well, a fluid running past a plate, right? So this is just a flow field, if you will, and this could be a liquid or a gas, but most of the time we're going to think about gases aren't nearly as viscous, so we could actually even just ignore them a lot of times. But there is viscosity, but let's think of them as liquids for now. And we have this flow, and over here before it gets near the plate, it's just free to move. But as soon as it encounters the plate, the closest molecule is going to stick to the plate and not slip. That's the no-slip condition, where there's zero velocity of that first molecule. He's like stuck to the plate. That's like and this is like the wetted area. Our characters wetted in vapes. But this is the wetted location, and so the first molecule sticks and doesn't slip. But the second molecule, we run him right after. You can't see it, right? This thing is not blown up big enough. But the second sticks and slides to the first. And that's the stickiness between the fluid molecules creates, and the relative velocity between them creates this viscosity, right? That's the stickiness of the fluid to itself. Now it's going to completely stick. The first molecule completely sticks to the plate. The second one sticks to the second one, but can slide, right? And another measure of viscosity, now this is how we typically measure as a practical manner, but another definition of viscosity is the slope. You'll see that because we start out at 0 here because of the no slip condition, and then the next molecule, the next, like different layers of molecules as they're slipping across to each other, they're going to create like this, what we call a velocity profile. And the slope of this velocity profile, and it depends where you are onto the thing, is the technical measure of viscosity. And we're going to cover this again, so we don't need to know all of that right here. But just this is like an introduction, so that there'll be some familiarity with it later on. So the practical, like, hey, I want to get this motor oil and find out the viscosity of it. There's a certain size funnel, a certain amount of volume of the oil, and then at a specific temperature they will pour it out and they'll time it, and that'll be the viscosity as you would get it reported on a can of oil. On the other hand, what we want is a viscosity actually becomes a slope, the slope of a curve on here. So let's see, let's see where I am. I'm going to pause. Okay, so I think that's enough for this video, because this too also took about 15 minutes. Let's see what the next one can do, where we're going to talk about different classifications of fluid flow. So I'm going to make these a little bit faster.